Okay, so hello everyone, and welcome to today's edition of our extremal and probabilistic combinatorics webinar. Let me briefly go through the usual technical stuff. This talk is being recorded and we will eventually post it on YouTube. If you have any questions, then I suggest either unmute yourself and pose the question, or if you have a problem with your audio, then write it in the chat, and if our speaker doesn't notice it, then I will read it out. And so now it's my pleasure to introduce our today's speaker, Jonathan Tidor from MIT. And Jonathan Tidor will talk about his recent nice results, which combine some extremal questions in geometry with graph theory. So please, Jonathan.
Thank you for that nice introduction. Thanks to everyone for being here. Let me just get set up. Okay, so today I'm going to be talking about some work I did on the problem of equiangular lines with a fixed angle. Everything I talk about today is going to be joint with Zilin Jiang, Yannick Yao, Shentong Zhang, and Yufei Zhao. And as Jan said, if you have any questions at any point, feel free to unmute yourself and ask. I'd be happy to take those questions. So let's start with a very simple problem in discrete geometry that dates back maybe to the 30s and 40s even. So we say that a collection of n lines through the origin in d-dimensional Euclidean space is equiangular if every pair of lines makes the same angle. So a very simple and natural question is just what's the largest size of a collection of equiangular lines in d-dimensional Euclidean space? So I'll denote this quantity by n of d. So I have some examples here to get us started. So n of 2, we're in two-dimensional space. And it's easy to convince yourself that the best you can do is you can take 3 equally spaced lines, forming an angle of 60 degrees each. And this will get you, 3 is the best you can do. In 3 dimensions, it's a little bit harder to figure out. But there's this nice example. You can take a regular icosahedron and take its 6 main diagonals. And then if you inspect this picture, you can see every pair of lines forms an angle which is drawn out by an edge of the icosahedron. So it makes the same angle. And though it takes a little work, you can show that this is the best possible example. So 6 equiangular lines is the largest size set you can make in 3 dimensions. So this image was drawn by my co-author Zilin, who's a much better artist than I am. So now determining n of d for larger values of d is quite an interesting problem and has been studied for a long time. So I've taken this table from a paper just last year by Greaves et al. And it shows the current state-of-the-art bounds. Note that a couple of these small ones, even dimension 14 and 16, are new results from last year. And once we get up to dimension 17, the right answer isn't even known. So there are people still studying this kind of problem, and there's lots of interesting work to be done here. But in this talk, I'm going to be much more interested in asymptotic results. So things like what's the order of growth of n of d as d goes to infinity. So the first result of this form, the first general bound, is due to Gerson, proven sometime in the 70s. And his bound simply says that n of d is at most quadratic. Specifically, it's bounded by d times d plus 1 over 2. And this is such a nice result. I think everyone should see the proof of it at least once in their life. So I'm going to start by going through the proof of this result, which introduces some very nice ideas. So the first step is to pick unit vectors along the lines. And you have a choice here. There are two unit vectors that point along the direction of the line. But for now, I won't care which direction you pick. So I get unit vectors v1 through vn in RD. And they have the property that the dot products, we'll say that all the dot products are plus or minus alpha. The distinct dot products, and of course, they're unit vectors. So dot product is 1 if they're equal. So here I'm just setting what the common angle is to be a cosine of alpha. So the main idea of this proof is to consider these rank 1 square matrices I get by taking the outer product of the vectors with themselves. So these are all d times d symmetric matrices. And maybe you can already guess where this proof is going. The set of d by d symmetric matrices is a d times d plus 1 over 2-dimensional vector space. So if we could prove that these n square matrices are linearly independent, then that would imply that there are at most d times d plus 1 over 2 of them, which is what we wanted to show. Now, one way to show a bunch of points in the vector space are independent is to compute all their pairwise inner products, if there's an inner product on that vector space. And there is a natural inner product on the space of matrices. So I'm just going to define this, sometimes called the Hilbert-Schmidt inner product, is defined to be the trace of the products. And sometimes there's a transpose here, but it won't matter because all my matrices are symmetric. So this turns this vector space into an inner product space. So let me just compute what are these inner products of the vectors I have. By definition, this is the trace of VI transpose, VJ, VJ transpose. And there are a couple ways you could compute this quantity, but maybe the slickest is to use the cyclic invariance of trace. And this new matrix I have here is a 1-by-1 matrix. So it's easy to compute its trace. It's its only entry. So this trace is just the dot product of vi and vj squared as normal vectors. And we know what this is. Well, we had a plus or minus alpha, but squaring that goes away, and the dot product is always alpha squared for I and j distinct. So this, so I can make what's called the Gram matrix of these n vectors, which is just the n by n matrix of their inner products. And this computation shows me that the Gram matrix is ones on the diagonal and alpha squared everywhere else. And you can check that this explicit matrix is full rank, which by some linear algebra implies that the n vectors I started with are linearly independent. Let me just write that down. So this is full rank, which implies these matrices are linearly independent. Which then implies the number of them is at most the dimension of the vector space they lie in, which is d times d plus 1 over 2, since they're symmetric d by d matrices. And this is exactly the bound we were trying to prove. So if there are any questions about this proof, I can take them right now. If not, let me move on then. So this was a general purpose quadratic upper bound on the size of a set of equiangular lines in d-dimensional Euclidean space. And it was quite a few more decades until we had a lower bound which came anywhere close to matching this. But this result was proven by Decane in 2000, I believe, which is he gave a construction of a set of equiangular lines, which does essentially quadratic growth. So combining this construction with the previous upper bound, we see that n of d is always quadratic, which essentially resolves the problem, though there's, of course, many more things you could ask, such as what's the right leading order. But I want to talk about a slightly more refined question at this point. So actually, maybe one piece of motivation is I can tell you that in this construction of Decane, the angle used goes to 90 degrees as the dimension goes to infinity. So as the as you take this construction larger and larger dimensions, the vectors get closer and closer and closer to being orthogonal. So one thing that could tell you is maybe it's an interesting question to fix the angle in advance and then take the dimension to infinity and see if you get different asymptotic behavior. And that's the question we're going to be studying. It turns out it's interesting, not just for this reason, but for a couple other reasons. So let me just write that down. I'm going to write n alpha of d to be the maximum size of a configuration of equiangular lines in RD with common angle. I'm just going to parameterize this by arc cosine alpha as a common angle. So studying the values of n alpha of d was a question that was even posed around the 70s as just a way to get at the value of n of d, because n of d is just the maximum of n alpha of d over all values of alpha. So if you can figure out this finite question, you solve the n of d question. And actually, surprisingly, there's this result of Newman, which is also one of the reasons I think it's interesting to study this n alpha of d, which says something quite interesting. It says n alpha of d is always at most 2d, as long as your alpha is not 1 over an odd integer, which is something kind of bizarre at first sight. How does this 1 over an odd integer come in? But also, we know n of d grows quadratically, though they didn't know that back in the 70s. I'm sure that was conjectured. N of d grows quadratically. But almost all the n alpha of d's are bounded by 2d. This tells you that in the whatever best construction, your common angle, your value of alpha has to be 1 over an odd integer. And all the other values of alpha can't possibly give a good construction. So this just leaves the question of, if you can understand n alpha of d for alpha 1 over an odd integer, you've essentially solved the whole problem. So there's some results, first by Lemons and Seidel in the 70s, that, so they studied the first open case, which is n 1/3 d, and they proved that this, they determined the exact value. It's equal to 2 times d minus 1 for d at least 15, and it takes some other values for the smaller values of d. And then in the 80s, Neumeier computed the values of n 1/5 d. It's actually equal to floor of 3 has d minus 1 for d sufficiently large. And then it takes some other more arbitrary values for the smaller values of d. And this is where people got stuck. We've bounded n alpha of d for all alpha not 1 over an odd integer. We've solved 1/3 and 1/5, and no one could figure out the 1/7 problem. So this is kind of where progress stopped for a while, until the problem found some more interest just 5 years ago with this work of Boris Buch. So Buch had the idea of maybe we could throw some, actually his new ingredient was applying some Ramsey theory to this problem. And he finally managed to resolve this problem by showing n alpha of d is linear for every value of alpha. So there's only nu for 1/7 and beyond, but he showed that this thing was always linear, which kind of resolves the problem of what is its growth rate. The main deficiency is that this leading coefficient, C alpha, has some quite bad dependence on alpha. I think it's maybe exponential in 1 over alpha or something like that. So this was followed up by a very nice work of 4 people, Bala, Draxler, Kivash, and Sudakov. who showed that n alpha of d is actually always bounded by 2d for sufficiently large d. So they bring this constant down to 2. So this gives you at least an upper bound on alpha, n alpha of d, for d large enough. Though it doesn't tell you what the true answer is, like in the 1/3 case and the 1/5 case, where the right answer is known. So that brings us to the result I want to tell you about today by myself, Zilin Jane. So it's a little bit technical to state what this result means, so I'll do it in a second, but let me just give one special case. We show that this n1/2k minus 1d, not an upper bound for it, but we give its exact value. Its exact value is the floor of k/k minus 1 times d minus 1 for all d sufficiently large. For the smaller values of d, I can't tell you exactly what it is, and it may take relatively large values there. But at large values of d, it eventually settles off to being this linear function, the floor of a linear function. So this is for alpha equal to 1 over an odd integer. And actually, for every value of alpha, we determine the value of n alpha of d for d large enough. It just takes a little bit more notation to state the general result. So actually, let me go through that notation now so I can state the full version of this theorem, and then I'll talk about some of the ideas which go into the proof, some of which are quite surprising. Okay, and this is the point in the talk where spectral graph theory is going to start to show up. So I start with some graph G, say the path of length 2. From the graph, we make an adjacency matrix, which I'm always going to denote A sub G. By adjacency matrix, I always mean the 0, 1 matrix of adjacencies, no like normalization or something like that. So in this case, this is the adjacency matrix. And then we'll be interested in the eigenvalues of this adjacency matrix. For now, just the spectral radius. That is the largest eigenvalue of A of G. So for the path of length 2, the spectral radius is square root of 2. Okay, and to state the theorem, I'm going to need this kind of strange spectral parameter that I'm going to call the spectral radius order. So the spectral radius order is defined to be the minimum number of vertices in a graph with spectral radius lambda, and infinity if no such graph exists.
So Jonathan, there is a question by Anurag who is asking whether these results for large D, whether you could pull them back and get any bounds on N.
Oh, that's a really good question. So right now, the answer is no, specifically because sufficiently large, I think, means doubly exponential. So you would have to improve what sufficient, so yeah, improving what sufficiently large means here would then possibly start to let you get more information about N of D, which would be a quite interesting thing to do. But right now, I don't know how. Good question. Okay, so I have just defined spectral radius order. Let me just give a couple examples because it's a little bit of a strange quantity. So for example, if I plug in an integer, I get just one larger than that. The smallest graph with spectral radius 1 is K2. The smallest graph with spectral radius 2 is K3. Smallest graph with spectral radius 3 is K4. But lots of other things, for example, K of root 2 is equal to 3 because of this example given just above. And you can compute this in general. So now the full statement of our main theorem is, let's see, I'm going to let alpha be equal to 1 over 2 lambda plus 1. Then n alpha of d is equal to floor of k lambda over k lambda minus 1 times d minus 1 for d sufficiently large. This is if k lambda is finite, and if k lambda is infinite, well, I can't tell you exactly what it is, but it's at most 1 plus little o of 1. So it's almost minimum possible value. So you can check that this theorem generalizes the previous one. It doesn't contradict it. Specifically because of these complete graph examples. Show you that the general theorem is an extension of the first one I told you, but the general theorem tells you lots of other things which are, unknown, and I'm not sure even anyone would have conjectured these things. One more example, like if I want to know n1 over 1 plus 2 root 2 of d, well, it turns out it's equal to 3 halves d minus 1 for d sufficiently large. Because of this computation earlier. Let me just point out that this leading order of growth was conjectured by Zhang and Polyansky just a couple years ago. And the first thing I want to do right now is talk about why this strange spectral parameter actually shows up as the right answer to this problem. So to do that, I'm going to go through some steps of the proof. The outline. Are there any questions before I get started on that? All right. So let's go through the outline of this proof. So the first step is to, as usual, pick unit vectors v1 through vn along the directions of the lines. And remember that there's a choice. That you can pick VI or you can pick negative VI. And at this step, it doesn't matter. And in the last proof, we didn't use this choice, but in this proof, we're actually going to make use of the fact that we have this choice. So this proof will also have a Gram matrix. So this is just, again, the matrix of all inner products. Of these n vectors. So the fact I need about this Gram matrix is M is positive semi-definite. And since it's the Gram matrix of some points in RD, it turns out that it has rank at most D. And these are actually the only two constraints. If you take any n by n matrix, which is positive semi-definite and rank at most D, you can come up with a collection of n vectors in RD such that this is the Gram matrix. So this is necessary and sufficient. I haven't lost anything yet. But note that this Gram matrix has a very specific form. It has ones on the diagonal. And then the off diagonals, well, has some plus alphas and it has some minus alphas. But those are the only two values it takes. So we can record all this information by defining a graph G. On n vertices, where I is adjacent to J if the dot product of Vi and Vj is negative. So I just chose one of the two possibilities and said negative alpha is edge, alpha is non-edge. And once I've done this, I can express the Gram matrix M in terms of the adjacency matrix of G. The precise formula I get, it turns out, is M is 1 minus alpha times the identity plus alpha times the all ones matrix minus 2 alpha times the adjacency matrix of G. So this is just some formula you can check. And let me rearrange this to get into a slightly nicer form. So all I'm going to do is I'm going to divide through by 2 alpha, and I'm going to set this value of lambda, which, mysteriously showed up in the introduction. This is in the theorem statement. This is where it comes from. Okay, so at this point, I've done some reductions, but they go both ways. I haven't lost anything yet. This problem that I started with is equivalent to asking, what is the largest graph G such that lambda I minus the adjacency matrix of G plus 1/2 J is positive semi-definite and rank at most D. This question is equivalent to computing n alpha of D, but now has a flavor of a spectral graph theory problem. Okay, so let me give an example. So here, let's think about this for a second. So lambda I is a full rank matrix, and J is a rank 1 matrix. Let me write this down. So we start with lambda I, which is very big rank. We're going to add 1/2 j, which is rank 1, so it's not going to affect the rank by very much. So subtracting off AG must decrease the rank by a lot, or else there's no way we're going to get down to rank D. So, and what that means is AG must have eigenvalue lambda with multiplicity, say at least n minus d minus 1, maybe n minus d, but something around this order. This is the only way that we're going to get down from rank n to rank d in lambda I minus ag. And furthermore, since this quantity is supposed to be positive semi-definite, this implies that lambda I minus ag has at most one negative eigenvalue. If lambda I minus ag has 0 negative eigenvalues, then when you add j, it'll still have 0 negative eigenvalues. And if you have one negative eigenvalue, possibly adding in 1/2 j will cancel it out, and you'll get something positive semi-definite. But if you have multiple negative eigenvalues, when you add in a rank 1 thing, you can't possibly get something that's positive semi-definite. So combining these observations, we get that either lambda is the largest eigenvalue of G, let me just write this as G, or the second largest eigenvalue of G. And in either case, lambda has very high multiplicity. Okay, let's start with this case because it's...
Jonathan, could you, I was a bit lost in this linear algebra part. So could you go through these 3 or 4 lines and sort of refer to the, for example, when you are saying that you must have one specific eigenvalue with large multiplicity. Okay, maybe it's some linear algebra triviality, but I don't see it, right? So you are subtracting 2 matrices, and now you are sort of looking to what happens to the rank, right?
Yeah, okay, thanks for asking. So we have... So we know that this matrix, lambda I minus ag plus 1/2 j, has small rank. So let's just look at the size of the yeah, let me... Good question. So if I plug in a vector v on the left-hand side here, well, I'm going to get lambda v minus ag of v plus this last term, but let's assume for now that jv equals 0, which I can do by only losing one dimension. So sorry, let me write this in a slightly different way. So we know that the kernel, the dimension of the kernel of lambda I minus ag plus 1/2 j is at least n minus d. That's the assumption. And the dimension of the kernel of 1/2 j is just n minus 1, since it's a rank 1 matrix. So the dimension of the kernel of lambda I minus ag is at least the dimension of the intersections of the two kernels. Which I can lower bound by n minus d minus 1, just adding the codimensions. So there's a large dimension space of things which are killed by lambda I minus ag, and this is an the lambda eigenspace of ag. I hope that was clearer than my first explanation. Yeah, okay, so this is the key point, that we have large eigenvalue multiplicity, and now, from now on, I just need to study what does it mean for a graph to have some top or second highest eigenvalue with large multiplicity. Okay, so we can start with the top eigenvalue case. And this is pretty straightforward due to the Perrin-Frobenius theorem, which says, among other things, the top eigenvalue of a connected graph occurs with multiplicity 1. So if we want lambda to be the top eigenvalue and occur with high multiplicity, well, then our graph needs to have a lot of connected components. So here's a construction. Let me call it construction as an example. So let H be the smallest graph with spectral radius 1. So that means, sorry, not spectral radius 1, spectral radius lambda. So that means it's a graph whose number of vertices is exactly the spectral radius order, since that's how we defined it. And then we define our graph G to be as many disjoint copies of H as we can fit together. It's not too hard to see that this is just the best possible construction of a graph with top eigenvalue lambda and high multiplicity. You just take the smallest possible graph with top eigenvalue lambda, and then you take a bunch of copies of it. And if you do this example and computation correctly, you'll see that this this gives exactly the bound I claimed with k lambda over k lambda minus 1. If you modify this very slightly. So the top eigenvalue case gives the right bound. So all I need to do is show that the second largest eigenvalue case cannot do as well as this asymptotically. And that's our main contribution. So let me spend a minute talking about second eigenvalue multiplicity. So just a question to start off. Can a graph have large second eigenvalue multiplicity? by, so this I just mean the multiplicity of the second largest eigenvalue of the adjacency matrix. And the answer is yes. Let me give you a handful of examples. So for example, I could take a bunch of disjoint small graphs. Here we have n times a path of length 2, and its spectrum is the top eigenvalue 1 occurs with multiplicity n, and the second eigenvalue -1 occurs with multiplicity n. So here, the second eigenvalue occurs with multiplicity half the total thing. Another example is I could take the complete graph where the top eigenvalue is n-1 with multiplicity 1, and the bottom eigenvalue is -1 multiplicity n-1. And there are a lot more examples like this. Let me give just one more. I could take the Paley graph GP, which is some pseudo-random graph. It has top eigenvalue p-1/2 with multiplicity 1. Its second largest eigenvalue is something which occurs with multiplicity p-1/2, and then its third eigenvalue occurs with multiplicity p-1/2. So here the second and third eigenvalues also have linear multiplicity. In general, all strongly regular graphs have only 3 eigenvalues, and the second and third eigenvalues occur with linear multiplicity. So it should be clear that, yes, there are lots of graphs with large second eigenvalue multiplicity. So our only hope is that somehow we can rule these graphs out from occurring in our construction. And it seems I'm kind of short on time, so I will not give you any details about this. But let me just say that if you restrict your attention to graphs which are first connected, and well, that rules out the first example. But if you also restrict your attention to bounded degree graphs, that rules out the second and third examples. And with just these 2 restrictions, your graph has sublinear second eigenvalue multiplicity. Let me write this down. Let G So the second largest eigenvalue multiplicity is at most, well, what we prove is some constant that depends on the bound on the degree times the number of vertices over log n. So just slightly sublinear. Let me see. So as long as you have these 2 conditions connected to rule out this first example, and bounded degree to rule out these next 2 examples, you get a sublinear second eigenvalue multiplicity. And then through a couple more steps, which I don't have time to describe, this gives d plus d over log d as the second case. So we can see that the first case is linear with a leading coefficient strictly bigger than 1. So the first case beats the second case asymptotically. And that's how we prove our theorem on an alpha of d. given this result about second eigenvalue multiplicity, which I think is quite an interesting direction. So I only have a couple minutes left. Let me mention a couple related problems to this second eigenvalue multiplicity result. Some related things. So you might ask, are there any connected bounded degree graphs with large second eigenvalue multiplicity? And the answer is yes. The simplest example is there's a four regular. So you can take a certain Cayley graph on the group PSL2Q. This is some highly non-abelian finite group. So you can take some four regular Cayley graph on it. And it's known that the second eigenvalue multiplicity here is on the order of n to the 1/3. So we get some fairly quick growth. So I think a great question is the right order of growth? Is there some power saving bound? You always get n to the c? Or is some n to the 1 minus little of 1 the right answer? And this does have some quite interesting implications on equiangular lines, exactly for the reason that Anurag asked about earlier, which is if you can improve this, this sublinear bound, then what sufficiently large means in our theorem statement gets improved, potentially to a very interesting regime. So there's been just a little bit of progress on this problem. A recent paper by Mackenzie, Rasmussen, and Srivastava gives a constant n to the log n to the 1/5, I believe, but only for delta regular graphs. So if your graph is connected in delta regular, then the second eigenvalue multiplicity is bounded by this n over log n, which is a quite interesting improvement. And I'd be very interested to see further improvements in this direction. So that's all I have to say today. I think now would be a good time to stop and take any questions anyone has.
So thank you, Jonathan, for a very nice talk. Before we get to questions, please unmute. I would ask people to unmute themselves and give Jonathan a round of applause. So if you have any questions, just unmute yourself and go ahead, please.
Just a comment. So apparently they have a new version of the paper, Mackenzie and like Srivastava, where they say it's not just for deregular, but also for, I think, maximum degree delta or something.
Yeah, no, so actually, I believe the second version of the paper is for the normalized adjacency matrix.
Ah, okay, my bad. I just saw it. Okay. Yeah, maybe, yeah.
It's an interesting, you could ask for all the variance in adjacency matrix, but I don't think it had any direct implication.
Okay, cool, thanks. Yeah.
Mm-hmm. So I see a question in chat. I believe it's actually been known for a long time that this d times d plus 1/2 bound can only be achieved in some very sparse set of dimensions. So it's already been ruled out for most values of D that you can achieve this upper bound. So it would be, I guess it's very interesting to say, can our techniques actually rule out D times D plus 1 over 2 in all sufficiently large dimensions? That is something I have not thought about. Yeah, that sounds like a very interesting direction, but I think it goes back to exactly what Anurag was asking about earlier, which is it would involve understanding how small we can get this sufficiently large to mean.
I have a question. I was wondering, what is the tightness of this bound? Meaning that, is there some natural barrier about how much the second largest eigenvalue can appear on the multiplicity?
Yeah, that's a great question. So I don't know exactly. I guess in general, I have no idea what the right answer should be for second eigenvalue multiplicity. There is a sense in which n over log n is a natural barrier, which is our proof uses what are called trace methods.
I think it's not the log n, right? Because the Mackenzie result already shows that it's n over log n at least. So there must be like something about it can't be log n.
So examples with irregular graphs that show n over log n is the right answer if you're asking not for the second largest eigenvalue multiplicity, but the multiplicity of eigenvalues in a small interval around the second largest one. It actually turns out for that related question, and if you're allowed irregular graphs, n over log n is the right answer. But that question is not really as natural as the original one. So I don't know about any implications for.
Okay, thank you.
Yeah, so I think this is maybe related to what you just commented on, but if I don't want a specific angle, but rather maybe a little window, but maybe an arbitrary set, can you still express, you know, everything is within a certain set of allowed angles, then this you can translate. Oh, you cannot. Okay. Right, so you can't translate it into with this fairly easy translation to graph theory, right?
So there's some issues. So this problem is sometimes called the spherical code problem. So there's some work on this done by in Boris Buch's paper and in the Bala Draxler Kivash Sudikov paper, and we have a follow-up paper which addresses some aspects of this problem, but the main thing is the part I skipped over due to time, so I didn't get to it. But I said it was sufficient to reduce to the case of bounded degree graphs in our problem, and I completely did not explain why. But part of it goes back to this line at the beginning, which is you have this freedom to switch from VI to negative VI. And that lets you do a lot of very clever things, including restricting to bounded degree graphs. So if your set of allowed angles isn't symmetric under negation, you can no longer do this trick and everything gets a lot harder. I guess you could ask about, you know, some simple sets which are symmetric under this negation. And that might be quite interesting, but I don't know about that.
Yeah, and somehow maybe a related question. So you have this choice of, of the direction, and now you have these graphs. So I wonder whether you could sort of explain whether there is something geometrically. I mean, I do see the translation. There are edges, non-edges, angles in this direction or in that direction, but I don't know what, or is there something your result says when you translate it back to the geometric setting? Is there some symmetry or something that you get from this?
I don't think so. There is something that's a little bit mysterious to me going on, which is when you switch to the second largest eigenvalue multiplicity question, you throw away some information, and you need some of it, which we get out of this switching VI to negative VI operation. But I can't give you like a complete classification of which graphs can pop out of this in a nice way, is the obvious way. But so I guess I don't really have a good answer to your question.
Mm-hmm. Or maybe if you can't say anything particular about the graphs, can you say something about the lines, that you could somehow group them, and they would be, some groups would be in some positions with respect to the other groups or something? I don't know.
Wait, actually maybe I can say something, which is, well, asymptotically, this first construction does much better than the second construction. So you should, if you're close to the maximum, you should have some large part which looks like this construction I gave. And then you should be able to translate that back into the line world and say what the lines look like. So maybe that's a better answer to your question.
Okay, thanks.